So this starts section 4.2. So the very first thing to talk about is something called the area problem. And what this involves is looking at a curve and figuring out what is the area underneath the curve. So how do we figure out the area contained within here? For instance, this is a problem that's been studied for quite some time, and it goes into a lot of different topics. Economists use it, chemists use it, a lot of different physical sciences use it. And the area problem has been solved over the years by first considering rectangles, sometimes of equal widths for ease, sometimes of unequal widths. But if we set up some rectangles with the curve here on the inside or the outside, we're getting something of an approximation of the area contained inside the curve. But it's not a perfect approximation because some of the area is missed, some of the area is overestimated, but it does allow an estimation to be done. So what was developed in order to determine the area is to keep making the rectangles smaller and smaller, making more and more rectangles until we're getting closer and closer to the actual area underneath the curve. And so the way this is accomplished is by taking the limit of the sum of the areas of each rectangle as the number of rectangles goes to infinity. So the more rectangles we have here to work with, the closer we can get to the actual precise area contained within the curve. And if we take the limit and use the concept of the limit in order to consider what happens when the number of rectangles just gets infinitely large, we're going to get the actual area contained within the curve. And so this gives rise to something called the integral. One way of interpreting the integral is the area within the curve. And so if we consider that our right endpoint is at A and our left endpoint is at B, then the area contained within the curve is represented by this particular symbol, which we call the integral symbol. And we say the integral from A to B of f of x dx is our notation. Since our curve is the f of x, in other words, that's our function here. And so this integral comes from the limit that I was mentioning above. The limit we say is n goes to infinity. N is the number of rectangles. And we say use this little symbol here which stands for summation. I equals 1 to n f of x I star delta x. Now there's a lot of stuff here, and we're not going to go into too much detail about it at the moment, but just to give you all a sense of why we're doing what we do here. This part here represents the area of each rectangle, and this part over here represents adding an infinite number together as the number of rectangles goes off to infinity. So it's a really kind of complicated thing to deal with in this format, but this is kind of what we're going to be looking at for a little while. This particular notation right here, we're not really going to look at the limit and the summation and all these things to do the calculation. We're going to learn about rules that allow us to calculate the so-called integral, which can always be connected back with the area contained within the curve. So before we go any further, let me just go through a little bit more about this notation. So this kind of looks like an elongated S, stands for integral. Okay, and again we're going to use two numbers A and B. Those are going to be two numbers on the x-axis, and we can have a curve which curves up from A, can curve up and down into various different things, and then stops at B, or we're only looking between the curve between the A and the B. So we say the integral, we put A at the bottom, we put B at the top, and we say that's the integral from A to B, is how we read that. Then next comes the function name, f of x here. F of x could be any function. And then at the very end we have this thing called dx. dx is kind of like what we had with the derivatives, but for the most part we're not going to go into too much detail about what that dx is going to represent to us. It's kind of coming from the area of each rectangle from up above and different things. But just remember that dx is always here. Okay? Sometimes we substitute things in for it, sometimes we can move it around, but otherwise we'll have something there for the dx. It kind of represents what variable we're using inside of our integral. So as I was saying, the integral from A to B is going to be representing the area within the curve. One thing that we do have when we talk about integrals is areas which are up above the x-axis are positive areas, and areas below the x-axis are negative areas. Kind of a weird idea, but we will get a negative area when we look at the area that falls below the x-axis. Now let's look at our first example of looking at this new notation for integrals and figuring out what they're equal to based off of the area contained inside the curve. So first one is the integral from 0 to 2 of f of x dx. Okay, now looking at the graph, we start at 0 and the last number is 2. So thinking about it this way, we're looking at the area inside of the curve between 0 and 2. Okay, so I'm going to figure out what the area contained within here is by using the shape that's contained inside the curve. And this area that we're looking at shaded in here is a trapezoid. Okay, so we can actually use the idea of finding the area of the trapezoid to figure out what the integral is equal to. Okay, the formula for the area of a trapezoid is 1/2 height, and then you add together the two bases, the big one and the small one, on the other two sides. So this side is 1, this side is 3, and this side is 2. And this is like our height, and this is like our two bases right here. So I can use those numbers, 1/2 times 2 times 1 plus 3. And if we do the calculation, that's going to come out to be 4. So the area contained between these two these two values of x is 4. And now we're going to figure out what is the integral from 0 to 5 of f of x dx. Okay, so now we're going to be looking at the area from 0 to 5. So now we're going to add in the area between here as well. We can include the area that we already figured out, which is the 4. And if I look at this trapezoid here, we can actually use that area. So we're going to have the 4 plus 1/2. And you'll notice this side over here has a length of 3. So we use the other two sides here to help us out with figuring out this area. It looks something like 1/2 times 3 times 1 plus 3. So let's see, that would equal to 4 plus 6, and that would be equal to 10. So what I just did here is figured out the area contained inside this trapezoid is 6. And adding those two together would get you the integral from 0 to 5. Okay, and then another integral will go for integral from 5 to 7, f of x dx. Okay, so now we're looking at the area. It's down now, dropped below the x-axis, and if you notice, that has the shape of a triangle. So we'll use the formula for the area of a triangle to figure out what this integral is equal to. 1/2 base times height. And so that area would be 3. Now the one thing to keep in mind is that this is falling below the x-axis, that area will actually be given by a negative number. So this integral would actually be -3 in this case. And then lastly, let's do the integral between 0 and 9 of f of x dx. So now we're going all the way to the end. We already have 4 in this section, 6 inside here, -3 in that triangle. The last shape at the very end will form another trapezoid. So we'll just consider finding the area of another trapezoid here. Let's see. So that'd be 4 plus 6. Those are the first two areas, and then the -3. The one that we're about to have to do will also be another negative, so we'll just put a negative there. 1/2 base, and then 3 plus 2. Those are the other sides, in other words. And so that would equal to 4 plus 6 minus 3 minus 5. Minus 5 is the area inside of this trapezoid, in other words. And so that would be equal to 2. So if we add together the positive areas up above, the 4 and the 6, and the -3 and the -5 for the other two areas, that tells us what the integral between 0 and 9 of f of x dx is equal to, the sum of all those areas.